Welcome back, everyone. So for the last part of this lecture, we will talk about batch normalization. So batch normalization is a technique that's very popular because it improves the rate of convergence of stochastic gradient descent by rescaling the values generated as internal layers of the network, okay, from the examples within each mini batch. So it's not really clear why this approach is effective at speeding up convergence, but it's very important in practice that you know how it works and why it's being used. And you will always find your neural network with batch normalization layers. So consider, for example, that we have a node Z somewhere in the network, and the values for Z, the values of Z for the M examples in a mini batch are Z1 all the way through Zm. Now, batch normalization will replace the Zi's with a new quantity called Zi hat, which is calculated using this formula, and we will discuss what each element of this formula is. So mu in this case is the mean value of Z across the mini batch. Sigma is the standard deviation of Z1 through Zm. Epsilon is a small constant added just in case sigma is 0, so we don't get division by 0. So we make sure, so sigma, we add in 0.001 to make sure we're always dividing by a non-zero number. And gamma and beta, these are the learned parameters of that batch normalization layer. So what this formula does essentially is that it normalizes the Zi's using the mean and standard deviation of the values as determined by the values of beta and gamma. So this means that the outcome is much simpler to train because it removes any bias in the original Zi's and provides you with nice standardized value Zi hat. So it makes it much simpler to train a deep network. So without batch normalization, information can get lost if a layer's weight are too small. At one point, if your network is very deep, we said with backpropagation, we have this problem of vanishing gradient. The gradient becomes too small and the weights become too small as you get further and further away from the output layer. The standard deviation at that layer decays to also becomes near 0. So what batch normalization does is that it prevents this from happening. It reduces the need for careful initialization as well of all the weights in the network to make sure that the nodes in each layer are in the right operating region to allow information to propagate. So with batch normalization, we usually include beta and gamma, which may be node specific or layer specific. So typically after each connected layer, we add a batch normalization layer all the way until we reach the output layer, which is obviously not batch normalized. So we're just adding additional parameters for the network to learn to optimize them, again using gradient descent, so that they are included in the learning process. So just two additional elements to the parameter vector omega W. After training, beta and gamma are fixed at the learned value. So when you get a new example and now you want to make a prediction, once the network is trained, you don't retrain beta and gamma, and we just use whatever values we got after finishing training. So now we discussed many types of neural network layers between fully connected layers, convolution layers, pooling layers, normalization layers, and so on. Now, your task then is to choose a network architecture. And the goal, you always have to keep that in mind, is that your goal is not really to fit the training data as best as possible. No, your goal really is to generalize to new data that has not been seen before, okay, as measured by performance on a test set that is brand new that the network has never seen. So now we're going to discuss some approaches that improve generalization performance, which is what we care about at the end of the day. So three main buttons we get to play with. The first one is, of course, to select the right network architecture. The second one is to penalize large weights. And finally, the last one is to involves randomly disturbing the values passing through the network during training, which is similar, leads to a result similar to ensemble training, which you have seen with classification trees before, where we essentially pick a random set of training points and a random set of features and train a tree, and then we combine all these subtrees together using some kind of voting mechanism. So we can generate some the same outcome here in neural network by randomly dropping down some neurons during certain iteration, and then let the network retrain again without these neurons and so on. So we will see that. So the first step then is to choose a network architecture. So your goal, remember, is to find the network architecture that will generalize well. And this is different depending on the kind of data that you're working with. Is it images? Is it speech? Is it text? Is it video? What type of data you're working on? So some neural network architectures are explicitly designed to generalize well on a specific data type. For example, convolutional neural network encodes the idea that the same feature extractor is useful at all locations across a spatial grid, and recurrent neural networks, on the other hand, encode the idea that same update rule is useful at all points in a stream of sequential data. So assuming these assumptions are correct, then we can expect convolutional neural network architectures to generalize well on images, problems that cover computer vision, and so on. Recurrent neural network, on the other hand, will generalize well with anything that includes a time series data, such that audio signals or translation, text translation, anything that involve data that comes in a stream over time. So one of the most important findings in the field of deep learning is that when comparing two networks with similar number of weights, the deeper network usually gives better generalization performance. So if you look at this figure, you can see this effect for one real-world application, which is recognizing house numbers. So you can see from this result that for any fixed number of parameters, so if you fix, for example, you say I'm using maximum of 20 million weights, you can see that if you split your 20 million weights over 11 layers, you got much lower test error than if you split the same number of weights over three layers. Okay, and so this result or this graph shows that for any fixed number of parameters, an 11 layer network is much better than a 3-layer network. Now, deep learning systems perform well on some but not all tasks. So for tasks with high dimensional inputs like images, video, and so on, they perform better than any other pure machine learning approach. So essentially, you could be using support vector machine or classification trees or anything like that to handle any high dimensional input. But this would require that you do a lot of feature engineering before feeding your input to your machine learning model. The good thing about deep neural network is that you don't have to worry about feature engineering because the layers themselves, they essentially engineer that for you. So this pre-processing was prevalent prior to 2010, but once the deep learning system came online, then people stopped doing all that feature engineering, pre-processing stuff, and just feed the raw data to the neural network and let it learn its own features. So deep learning models then are very capable at doing all these pre-processing steps. In particular, their success, leads us to believe that the task can be solved by parallel programs with a small number of steps. So this is very important as well because, as we saw with stochastic gradient descent, it's an ideal situation for using a GPU or a TPU because we can run the batches in parallel, which is not something we can do with other machine learning approaches. So although deep learning models generalize well in many cases, sometimes they can overfit a specific problem. Okay, so or they generate errors that we didn't expect. For example, their output could be discontinuous, so that a small change in an input can cause a large change in the output. For example, it may be possible to just change a few pixels in an image of a dog, and then you see your network classifying the dog as a cat or a school bus. Okay, so even though you only changed very few pixels and the training image still looks exactly like a dog, but the network got fooled and misclassified it. This type of example where we take a training point and intentionally change some pixels to make it harder for the network is the foundation of adversarial training, which I believe you will do an assignment on it either this week or next week, sometime in this class. So when adversarial examples like what we just discussed were first discovered, people started developing algorithms to use them essentially to improve the training of the network and to improve its performance as well. And that's what led to this adversarial neural networks that you will learn about. Okay, we continue in the next part.